Okay, welcome back. The first talk this afternoon is Chris Schafhauser with 1F, Tracially complete C-star algebras.
Thanks, Brad. And yeah, first let me thank the organizers for the invitation. And also I should say this is joint work with several people, which we hope to have it available for too long. So Jorge Castejos, Jose Carrion, Sam Evington, Jamie Gabe, Aaron Taquishas, and Stuart White. Right. And so we'll start off with some motivation of what we're doing here, and start out with somewhat vague motivation, but so there's a standard theme in C-star algebras, which I guess goes back in some form to the beginning of the subject. Yeah.
This thing actually blocks.
Oh, should I switch it? Actually, maybe I can just move to the, yeah, this will work. So there's a standard theme that goes back probably in some form beginning of C-star algebras, where you can study C-star algebra, say A, by studying its von Neumann algebra completion. So you represent A somewhere. And then take the strong closure or double commutant of A in some representation, some or all representations. And one of the most famous forms of this, or famous results along these lines, A is nuclear, so it has this CP factorization through finite dimensional things. Approximately computing pointwise in the norm topology, if and only if the von Neumann algebra generating the universal representation, which is the bidual, is, let's say, semi-discrete or injective, hyperfinite. They all are be equivalent, but so the analogous but in some von Neumann algebra topology, let's say weak star topology, or strong or weak operator topologies, it comes out the same condition. Right. Okay, so the tracially complete C-star algebras, this grew out of really studying regularity in classification problems, and in the stably finite setting, where the representations that are of most interest there are the tracial ones. And you want to try to say something about the C-star algebra by studying its tracial von Neumann algebra completions. And give some more modern forms of the passing from von Neumann algebras to C-star algebras. I'll try to collect several of these here. So suppose, let's say A is say separable, simple, unital, nuclear C-star algebra. For now, I'll assume it has unique trace. Throughout the talk, I wanted to have at least one trace. For now, we'll talk, like most talks, about what happens if there's not a unique trace, but several of them. And let's say with strict comparison. So, okay, so like typical example, C of X cross, let's just say, C of X cross Z for a minimal uniquely ergodic action. It's a unique invariant measure. where X is finite dimensional. Or you can do this for far more general group actions under various hypotheses, but stick with this. So let's flip these. And let's say let M be the von Neumann algebra coming from the GNS representation of the unique trace, which at the end of the day is the hyperfinite 2-1 factor R by Kahn's theorem. But going further back, there's, en route to Kahn proving injective implies hyperfinite, he collects many properties of injective 2-1 factors. The first one, so in this setting, M is McDuff. So this whole side is going to be, whole side of the board is going to be Kahn. Paper. On the C-star algebra side, under these assumptions, you do have A is Z-stable. This is Matui and Sato, about 2012. So in the Z-stability, it's often said as a direct analog of McDuff's property for 2-1 factors, and there's even, we can find remnants of the, the proofs of these are even very analogous in many places. That so somehow really is a C-star algebraic version of Kahn's result injective 2-1 factors are McDuff. Other properties you get, for instance, M is hyperfinite. There's, I guess the direct analogy would be A is AF. That's almost never gonna happen. Even for the C of X cross Z, it's just never an AF algebra. But there's a sort of a several colored version of hyperfiniteness, which is finite nuclear dimension, which does hold under these hypotheses. In this case, it's Sato, White, and Winter from, I think, 2015. So it's, in fact, more, it's, I think the original bound was dimension at most 3, and then more recently dropped to 1 by Castillo, Sevington, Tequicius, White, and Winter. But again, it's maybe just a couple more. There's and Kahn's theorem, every injective 2-1 factor embeds into the R omega, the ultrapower of the hyperfinite 2-1 factor. It's trivial once you know M is isomorphic to R, but he proves this on the way to proving M is isomorphic to R. It's really a key portion of his proof. And there is a C-star algebraic analog of this that, let me just write in, then I'll say more. So where Q is the universal UHF algebra, and now instead of a tracial ultrapower, it's a norm ultrapower. So this is does require A satisfy the UCT, but and the final one I'll say, as I mentioned several times, you take this A and complete it, it is always an injective 2-1 factor, and these assumptions, there's only one, it's R. C-star algebra side, there's certainly not a unique one of these. There's not even a unique UHF algebra, but up isomorphism A is determined by its ordered K-theory groups. Again, this requires A satisfies UCT, and I guess probably 2015 is when the final pieces came into place here. But yeah, and the one way I want to make, so there is this on the surface, you can draw analogs between what was happening in the case of the simple injective factors and simple nuclear C-star algebras. But even at the technical level, throughout the proofs, there are these close analogies and more. So every result on C-star algebra side makes heavy use of the analogous result on the von Neumann algebra side. But a lot of these come down to one way or another is, here all these are, on the left-hand side, all these are approximation properties with respect to the 2 norm coming from the trace. Here they satisfy analogous approximation properties with respect to the operator norm. And much of what this comes down to is making heavy use of strict comparison to somehow relate the operator norm and 2 norm estimates. And there's obtaining some, especially in these last couple, obtaining some non-stable K-theory of the algebra of 2 norm null sequences modulo operator norm null sequences. Okay. So they want to talk about is, this is all when there's unique trace. I want to strike out that hypothesis and keep the rest. So what happens if A has several traces? And I mean, there's, of course, you want to consider all the tracial von Neumann algebra completions. That's right, T of A for the tracial states. And you don't want to necessarily consider them individually. I mean, you want to organize them somehow, taking into account the geometry of the traces itself. It's some compact convex set. It's a case simplex, and they somehow they're trying to think of these things as being these von Neumann algebras as being fibered over this simplex of traces in some way. And there's the most natural approach to this is to take, the first thing that maybe comes to mind is you could take, the direct sum of all the, the same sort of way you would build the universal representation, look at the universal tracial representation, just take a direct sum of all the GNS constructions of overall traces. So that acts on now some giant Hilbert space. Represent A there and complete. What you get is exactly the finite part of the bidual. So still a von Neumann algebra, bigger than it's not a factor anymore unless there's a unique trace, but some finite von Neumann algebra. And it does, in a way, encode all the information that it's suggesting, where all the individual pi taus are canonically direct summands of the finite part of the bidual. There's a natural bijection between traces on A and normal traces on this thing, given by just taking normal trace in the bidual and restricting it back to A. But for somewhat subtle reasons, you actually do lose, quite a bit more information than you want in this completion. We're going to lose some information, like all the K-theory, but I'll keep the hypotheses up for now. But let's, so it's it really comes out of consequence of Kahn's theorem that classifying really injective von Neumann algebras as separable pre-dual. Take classification injective vectors.
Non-separable AF phenomenon.
Yes.
Okay, but my contribution is the non-separable case is very, very much.
Right. Yeah, it's sorry. Sorry, I didn't mean that. Yeah, what I mean, yeah, that's. Yeah, but I was gonna say, yeah, it's really so Kahn gave the, classification of separately acting injective von Neumann algebras. George pushed it to the non-separable case for things of that form, and I think more general even. But yeah, probably any in hyperfinite or AFD finite von Neumann algebra, or yeah. But so version I'll go here is say A and B are say separable nuclear, which will force these things to be injective, and now this could be relaxed if you change the statements a little bit, but say no finite dimensional representation, so I don't try to claim R is isomorphic to M2 or something. But the finite parts of the bidual are isomorphic if and only if the traces are isomorphic, but not as in a suitable way. It's an affine measurable function with affine measurable inverse. And so you lose the point is you forget the topology on the traces. You remember the REL structure generated by the topology, and then some general Choquet theory kicks in. That's actually equivalent to the extreme points of the traces on A and traces on B have the same cardinality. So when you pass this finite part of the bidual, you really lose almost all the structure of the traces. All you remember is how many traces there were according to some counting convention, how many extremal traces there are. So, yeah. Well, that's non-separable. I do want the algebras to be separable. I don't know how I wouldn't be surprised if it's necessary to get this last implication in, because Choquet theory gets complicated outside the metrizable setting. But yeah, so I'll keep the algebra separable, but the points of von Neumann algebras that we're considering aren't, which is why you need more than just Kahn's theorem. Right. So so probably I want to talk about is you want something that want some completion of A, which captures T of A, including its topology. And somehow it's a little bit more rigid than the finite part of the bidual, maybe, but not so much more rigid that you can still, you want K-theoretic obstructions to go away. You want some kind of tracial von Neumann algebraic techniques to work, but still has some von Neumann algebra-like behavior. Yeah, so it's you can drop finite dimensional representations if you remember, each extremal trace generates some factor. You have to encode the dimension of that factor, and the number of one-dimensional traces equals on both are the same, and the number of two-dimensional representations on both are the same, and so on. And then you could drop no finite dimensional representations. That's more or less what this is doing. It's disintegrating this over the whole trace simplex. No. It could be any metrizable simplex. So for instance, space of probability measures on a compact metric space can occur.
And then you're doing the direct sum over all the traces.
Well, I'm taking a direct sum of the Hilbert spaces they act on. This itself isn't a direct sum of all the completions. Oh, is it? Okay. Okay. Yeah, I didn't know that. I don't know its reference. But. So I really.
So just to be sure, you're saying that if you take the direct integral decomposition of this phi u, the fibers will be indexed by the gray space. They will be just right.
I mean, it's not actually. It is. This typically won't have a faithful normal trace, so you can't. I mean, it's usually sufficiently non-separable if there's not actually a direct integral decomposition, but it's. In some sense, it is. I mean, if you're willing to ignore some of the measure theoretic technicalities, it is more or less disintegrating A over the extremal traces. So I guess your base space is the space of extremal traces.
I guess it's non-separable, so there is no direct integral decomposition.
Right. Yeah. It does decompose as a measurable field. I mean, there's a measurable field of von Neumann algebras over the extreme traces, and you have to choose a measure to figure out which sections you want to talk. But. Yeah. Yeah, I mean, all this is, of course, in hindsight. It's coming on close to 50 years now. Yeah. But anyways, so what I want to do is look at some notion, something that sort of sits in between A and this universal finite von Neumann algebra completion that captures more of the traces. We're going to do it by building basically a different topology on A to complete with respect to. I mean, these biduals somehow loosely the strong operator completion in some representation, and it's of course norm complete to start with. We want something in between. So to find so you can find a uniform 2 norm by, it's all right, 2T of A. By taking each trace generates a 2 norm, which is 1 coming in the GNS construction, for instance. And I want to take the supremum overall of the 2 norms over all possible traces. So this is. Say trace, say star A, square root. So that's, well, I'm going to call it a norm. It's really a semi-norm. It's fine. You can, in general, but you can quotient by null vectors and view it as norm if you'd like. But so you have it's this uniform 2 semi-norm I want to consider. And I'm being sloppy with hypotheses, but the thing I really need to make this work is that the tracial state space is compact. For instance, phase unital, that's automatic. So let's just say A is unital for convenience. And then any unital C-star algebra, I can do this. Right. So where is this coming from? In a tracial von Neumann algebra, if you just fix a single faithful normal trace in your von Neumann algebra, the 2 tau topology induces a strong operator topology on bounded sets. And convergence, at least on norm-bounded subsets of the finite part of the bidual, strong convergence is really 2 tau convergence pointwise over tau. So now it's 2 tau convergence uniformly over tau. So you're somehow looking at the strong convergence in each von Neumann algebra completion, but uniformly over all choices of completion. Is what this topology is giving you. And it's a completion of A in this topology that I want to consider. And you have to be a little bit careful. I mean, of course, if you have a norm or a metric on a set, you can always complete it. Say, I don't want to just take the straight up completion of this thing. We need the unique trace space. You start with your C-star algebra and trace. The two-norm completion is not an operator algebra. It's a Hilbert space. So it's not the whole algebra you want to complete. So you want to complete norm-bounded subsets of the algebra, which you can do, right at A over bar T of A. So the completion, of course, usually it's all Cauchy sequences modulo all Cauchy sequences modulo all null sequences. Here I'm going to take the norm-bounded two norm null sequences or Cauchy sequences. Modulo the operator norm bounded two norm null sequences. I mean, there's some work to do to show it's actually a C-star algebra, but it is. It does actually depend that you're using traces, not states. But the numerator is a C-star algebra. The quotient, or the denominator is a closed two-sided ideal. I'll give you some idea of what the kind of things that can appear here. If you start with just a single, if you go back to unique trace setting, this that is just the von Neumann algebra completion in the unique trace, and in a way that preserves the copy of A inside both sides. Okay. Let's make it more interesting example. You take continuous functions from, say, a compact Hausdorff space K to the Jane-Sue algebra, or if you don't want to think about Z, replace it with UHF algebra, and it comes out to the same thing. This is uniform tracial completion works out to be, well, let me just write it. And it's all norm-bounded functions from K to R, which are continuous when R has a strong operator topology. So you do the expected enlarging of the fiber algebra, the Z or M to infinity gets replaced with its von Neumann algebra completion, but you also change the continuity condition from norm continuity to strong continuity. So you get a much more complicated algebra there. Hyperfinite to one factor. The line below is a definition. The bounded strongly continuous functions. Continuous when R is given the strong topology. For instance, this sigma, where by definition I mean this. For instance, this thing has no projections if K is connected. The thing on the right will actually have several, and it takes some work, but it even has non-constant projections.
Exactly what you could put in that second, you said, Jane-Sue algebra or algebra, it doesn't matter.
A weakly dense subalgebra of R. So nuclear unique trace, type 2, yeah. Yeah, nuclear unique trace with the trace not being finite dimensional would. No, it's if it sits inside R, it's yeah. And okay, this one's a rather deep theorem, but along the same lines. So aside from this flexibility of changing what the codomain is, you could also imagine, taking some twisted version of this where take some fiber bundle with fiber M to infinity where it's kind of like it's twisted it's moved around K. It won't change the completion still. And in fact, if A is separable, nuclear, say Z stable, with T of A is a compact convex set, happens to be the probability measures on some compact space K, or abstractly, it's that the extreme points of T of A form a weak star compact set, and then that's K is taken to be that compact set. Then the completion is still the same thing. So even if you start with the very twisted bundle over M to infinity, or even something that's not quite a bundle, but just has traces that look like it is, its completion will all collapse to the same algebra. Yeah.
If you take some probability measure on K, the von Neumann algebra completion, what you get exactly?
You get the expected thing. It'll be the direct integral of the fibers over that measure on the base. Yeah. And I'll get to the theorem, which so you need a special case of a special case of our theorem here. If this thing that's happening in this third example of Zawa is sort of, you're somehow, when you take the completion, you're forgetting, say, a nuclear Z stable algebra, you're forgetting everything except for what the traces look like. I mean, everything, if the traces are probability measures in K, all possible completions, no matter what algebra you plugged in, it collapses to the same algebra. And without restrictions on what the traces look like, we don't have quite as nice of a model for what the algebra is, but the same sort of thing happens. These uniform tracial completions are the same if and only if the trace simplicities are the same. Or now, I guess the bidual version I just erased. The defining part of the bidual is if and only if you have an isomorphism, and as a Borel affine isomorphism. Now it is, remembering the topology, so an affine homeomorphism between traces. Yeah, let's make them unital. What I really need is these to be compact, but yeah. So a non-unital case would be fine if you assume traces form a compact sets. There's not a good theory at the moment for when the traces themselves aren't compact. Right. I'll make that one. And the second, which is actually a corollary of this, you get a version of, amenable implies hyperfinite as well, that this tracial completion is approximately finite dimensional. So there's an increasing sequence of finite dimensional subalgebras with union being two norm dense in the tracial completion. I got a little bit small on the subscript there. I mean, the second one is corollary of the first, because it's a result, I think it's due to Bruce, that traces on any C-star algebra can be realized as traces on a simple AF algebra. So you start with your A, choose B to be AF with the same traces. Then the isomorphism tells you the finite dimensional approximations of B are finite dimensional approximations for A at level of completion. Right.
You said something about it still has non-Lyman A-like behavior. So what is the behavior?
Yeah, last 50 minutes or so, I'll say more. But this is basically Kahn's theorem. So that's one von Neumann algebra-like behavior, that the uniqueness of the injective 2-1 factor versus the amenable things are determined by what their traces look like. Factors, of course, have the unique trace. There's only ends up being one, but. So yeah, this is stated here, could have been dug out of earlier work of Castillos, Havington, Quacious, White, and Venter. But what we really started with these tracially complete C-star algebras. It was a question, if you start with the C-star algebra A, you take this uniform tracial completion, what kind of algebra will fall out of it? This thing typically, I mean, it's a C-star algebra technically, but it's huge. It's, and even the unique trace setting, it becomes a 2-1 factor. It's generally not a von Neumann algebra, as you can see from the example in the upper right. The center of that thing is C of K, which is usually projectionless. And the fact that center doesn't have many projections also rules out things like AW star algebras, or sequentially closed algebras, all these other various in-between things. So for some, part of what you want to do is axiomatize what kind of algebras are these things and how do you study them abstractly. And yeah, I was being sloppy with that. A priori, it should be a C-star isomorphism, which is continuous in the uniform 2 norms. It's actually under a Z-stability construction. It's a result of Sam Evington that any C-star isomorphism is automatically continuous in the 2 norms. So you can interpret the left-hand side as just a C-star algebra isomorphism.
So the traces would be the traces that are continuous in the 2 norms?
That's true. The traces are even without the Z-stability, it traces on T of A is going to be T of A will be in bijection with the 2 norm continuous traces here. Under Z stability, our work plus follow-up work of Sam showed the T of A is exactly the traces on that thing. That needs Z stability. We don't know it otherwise, but we
can find the right-hand side. That should be relatively straightforward, right? Because the traces are compact.
Left implies right. That's where you do need to know. If you interpret the left-hand side as a two norm continuous homeomorphism, the forward direction is trivial. Yeah, so it's the backwards direction that, yeah. If you interpret that just as an isomorphism of C-star algebras, that direction is also hard, but yeah. Okay. I mean, if this just means a C-star algebra isomorphism, that direction is actually hard as well. If you interpret it as a it is true, but yeah, if you interpret it as a 2 norm continuous C-star isomorphism, the forward direction is trivial. Yeah. Okay. So about 10 minutes left. Okay. So the object in the title there was really an attempt to to axiommatize, when you take these uniform tracial completions, what kind of things do you get? And it's a bit subtle that you start with, we built this thing by completing the unit ball in the 2 norm. We took this uniform 2 norm, completed its unit ball, and then took the span. So natural axiomatization of these things seems to be a unital C-star algebra where the unit ball is complete in the 2 norm. But with that definition, we don't actually know if the 2 norm completion is 2 norm complete in general. There's issues that when you pass this completion, you added a bunch of traces a priori, so that 2 norm changed. So tracially complete C-star algebra is, say, a unital is a pair X where M is a unital C-star algebra. And X is a compact convex set of traces, not necessarily all of them. So that I defined the 2T of A norm and the 2X norm by just swooping over X instead of all traces. This is a norm as opposed to a semi-norm. So non-trivial condition is positive definite here. And the ball, unit ball, the operator norm is complete in the 2 norm. For what's worth, I put unital in the definition, but you can actually prove unital from the other things if you want. So it's the compactness of X that's forcing things to be unital. So this is.
You briefly mentioned that. Shouldn't it be that Tracially complete C-star algebra is just a C-star algebra which is isomorphic to its tracial completion?
That's the problem. We actually don't. I don't think it's not even clear anything exists. We do have examples by now, but there's the problem is you take the C-star algebra A, you take its tracial completion, you've a priori added many traces to the completion, so you've changed what this 2 norm is. If you're defining it swooping over all traces, well, give me 2 minutes. I can say something.
The answer is you can't just say that.
Well, we don't know is the answer, I guess. There's which we've been calling the trace problem. That's not, I can't take this quite yet.
Chris, I'm actually gonna mention it later if you want to know.
Okay, go to Andrea's talk in half an hour. The basic rule is we don't know exactly what the connection, X might have to sit somehow very tightly inside T of M. It's, there's a lot of questions about exactly what X can look like. Before I give some examples, let me make one more definition. There's, actually, if you take X to be a point, this is exactly a tracial von Neumann algebra. I mean, there's this abstract characterization of tracial von Neumann algebra is that it's a unital C-star algebra with a faithful trace so that the unit ball is complete, two-norm complete in the two-norm of that trace. And then the GNS construction becomes an isomorphism, and that trace you started with was necessarily normal. So the one trace case collapses to the theory of tracial von Neumann algebras. Of course, in von Neumann algebra world, people pay most attention to the factors. There's the key notion is the ones we really care about are the factorial ones that I want X to be a face inside T of M. So if you take two traces and their average belongs to X, both already started in X. That does characterize factors in the von Neumann algebra setting. And it's, for the sake of proofs, it's very helpful to have a sort of geometric definition like this, but it is equivalent to maybe a more naive definition. You can think of these von Neumann algebra completions of M with respect to traces in X are somehow fibered over this convex set X. And because of the convexity, it's really the extreme points that should be the relevant things. So we all know is if you take a tracial completion, it's a factor on every extremal trace. So the tracial completions of M are all somehow built of the factor tracial completions of M. Is the factorial condition. Okay, since I have just a couple minutes, there's the algebra I started with here, the uniform tracial completion of a C-star algebra, with the distinguished traces being the one that came from the two-norm continuous extensions of the traces you started with, is factorial and tracially complete. I mean, the reason, and this is the kind of algebra that we actually cared about, the reason for not building part of the reason for not building factorial in the definition is we want that to count. And there's our reasons that Andrea will probably say more on of why we wanted to move outside the factorial setting sometimes. But okay, the 2 minutes. So we'll say much about what exactly we do here, but the basic problem we want to do is the basic problem we wanted to so these von Neumann algebra-like conditions, I want to know if I can prove some property on every von Neumann algebra completion of M, then I can, with say an approximation property with respect to, let's say a two-norm approximation property. I'm thinking like approximate, existence of approximate polar decompositions of elements, some approximate form of existence spectral projections, real rank 0, stable rank 1, big stuff. I want to know if such a property holds in every tracial von Neumann algebra completion, that it held uniformly over the traces. And the basic theorem, which I won't say anything close to rigorous here, is that it's possible under a suitable notion of property gamma. It's property gamma that there's, say, a approximately central projection of trace a half. I want to be able to do that not just in a two-norm of a single trace, but in the uniform two-norm, an approximately central projection of trace approximately a half. You need something a little bit stronger than that to make for the actual definition, but okay, and I'll say out loud. But we were able to, from the rigorous form of whatever this theorem actually says, is how we are able to prove structural properties of these uniform tracial completions by taking well-known properties of Neumann algebras and moving them to these tracially complete C-star algebras. And then it's with enough strict comparison, you can start turning uniform tracially complete C-star algebra properties back into, operator norm C-star algebra properties, modulo some K-theoretic conditions. But the biggest thing we do in this level is a version of the theorem above, that if you have in this uniform tracially complete setting semi-discrete factors with property gamma are hyperfinite, and two semi-discrete factors of property gamma are determined by their traces. The major question is, does gamma follow from semi-discreteness, which is actually become the last remaining part of the Thom's-Winter conjecture. Does this property gamma hold automatically in the nuclear setting? But I'm over time already, so I should stop. But thank you.